Hello students, today we'll discuss about acceleration due to gravity and factors affecting it. So my first topic is acceleration due to gravity with certain height h. Okay, so let us draw a figure. Suppose Earth and suppose its radius is r, and as we know, at the surface of Earth, acceleration due to gravity is taken as g, which is 9.8 meter per second square. And suppose this point is O, center, and this is A at the surface. And suppose we want to calculate acceleration due to gravity at certain height h. So let us consider a point B where we want to calculate acceleration due to gravity, and it is at h height from the surface. Okay, now as we know that acceleration due to gravity is given by the formula gm by r square, equation number 1, and this is the acceleration due to gravity at the surface, so we can write it as ga or simple g, which is 9.8 meter per second square. Now as we want to calculate value of g at point B, so suppose it is gb, and it can be written as gm, which is same mass of the planet. And now distance, actually here r is the distance of object from the center of earth. So if we consider object at the surface, then this distance is equals to radius of the earth. But if object is placed at point B, then the net distance between center of the earth and the object will be r plus h. So we can write here r plus h whole square. Now by dividing it gb by g, we get r square upon r plus h whole square, or we can write here gb equals to g r square upon r plus h whole square, or gb equals to g r upon r plus h whole square. So it is the formula for acceleration due to gravity at certain height h, and we can get the simplest form of this formula by considering some approximation. And let us consider that the height is very less than in compared to the radius of the earth. So it means we can consider that h by r is very less than 1, right? So by this equation, by equation 2, we can write gb equals to g r square upon r square 1 plus h upon r whole square. And now it can be written as simply g 1 plus h upon r whole power minus 2. Now as we know by the binomial expansion that 1 plus x whole power n can be written as 1 plus nx plus n into n minus 1 upon factorial 2 x square, and n into n minus 1, n minus 2 upon factorial 3 x cube, and so on. So here when we expand this bracket by using binomial expansion, we get the higher power of x, and since if we compare this equation with this bracket, then here x is h by r and n is minus 2. So when we expand this bracket, we get the higher power of h by r, h by r whole power 1, then minus 1, then minus 3, minus 2, or 1. So actually as we know that as our from our approximation, we have considered h is very less than r, and h by r is also very less than 1, then we can write that the maximum power of h by r, h by r whole square, h by r whole cube, they will also be very less than 1, right? So we can negligible, we can neglect the higher power of this term. So simply when we expand this bracket by this formula, we can write here GB equals to G 1 plus x whole power n, 1 plus x whole power n. So here n is minus 2 and x is h by r. So 1 plus nx, 1 plus n, what is n? N is minus 2, and x, what is x? X is h by r, and the next term will be h by r whole power square. So we can neglect it since it will be very less than 1. So simply we can write this formula as GB equals to G 1 minus 2h upon r. So gravity at any height h can be written as simply G at any height h, G 1 minus 2h upon r. This is the formula of gravity at any height h. By considering this, that h is, this height is very less than the r. Okay, so here we can find the gravity at any height h by using this formula. And if we want to calculate percentage change in gravity, so this can be find out by percentage change. As we know, percentage change in any quantity can be find out by final minus initial upon initial into 100. Simply change upon initial into 100. So final at any height gh, it can be written as g 1 minus 2h upon r minus initial at surface, it is simply g and initial into 100. So when we multiply this, then g will be cancelled out, and here the remaining term will be minus 2h by r into 100%. This minus sign shows that as we go up with height, then g will decrease with height. So it means at the surface g, which is 9.8 meter per second square, will be greater than at any height h. Right. Now simply by this equation, GB equals to G R square by 1 R plus H whole square. So here if we write the net distance between object and the center of the planet, it is r, small r. So here small r will be r plus h. So if we by the equation 2, we can see that g at any height h is inversely proportional to 1 by r square. Here r plus h can be written as small r. So when we plot the graph letter between g and the distance r from the center of the planet, then this will help us in plotting graph. GB is inversely proportional to small r square. Small r is the net distance between object and the planet. And now we are going to discuss acceleration due to gravity at certain depth d. Acceleration due to gravity at certain depth d. Now again we are considering Earth of mass m, and mass of the Earth is m, and its radius is r. And here let us consider a point A at the surface and center as O. And now we are going to calculate acceleration due to gravity g at certain depth d. So let us take a point B at certain depth d. Right. So remaining distance will be r minus d. Right. Now we have to calculate g, small g, at point B. So first we write the acceleration due to gravity at surface g is simply gm by r square, equation number 1. Now at point B, when we write the formula for acceleration due to gravity by the planet Earth, then it will be gm by r minus d whole square, right? No, actually there is one problem, that when it will be at depth d, then the net effective mass of the Earth which exert the gravitation on the object placed on B, it will be not complete m, it will be certain mass. Suppose it is m1. means the gravitational force on the object by the earth, it it will be due to the m1 mass of the earth. So here when we are writing GB means gravity at point B, which is at depth D. So here we'll write Gm1. M1 is the effective mass of the earth which is applying gravitational force on the object when it is placed at point B. So here GB will be Gm1 upon R minus D whole square. Now if we divide equation 2 and 1, then there is a problem between masses, and so actually uh, we should use the formula of G in terms of density, because we can assume that the density throughout the earth remains constant. So here by dividing GB upon G, we'll get m1 upon R minus D whole square into R square upon M, right? So now simply we want to find out the expression for G in simplest form. So we are going to write mass equals to volume into density, and as we always consider earth as a uniform sphere, so volume of a sphere can be taken as 4 by 3 pi r cube into density, suppose it is rho, right? So here we can write mass m1, and mass m1 is the sphere of radius r minus d. So when we write the expression for m1 in terms of density, it will be 4 by 3 pi r minus d whole cube rho, volume into density, upon r minus d whole square into r square upon mass, which is the whole mass of the earth. So 4 by 3 pi r cube into rho, 4 by 3 pi, 4 by 3 pi, rho, and here the power 2. So remaining will be r minus d upon r. So we can write G at any depth d is G 1 minus d upon r. So it is the expression for acceleration due to gravity with depth d, and we want to find the dependence on of the gravity on the distance, net distance from the center. Then it will be um, small r will be r minus d. So from this we can write small acceleration due to gravity at depth d, it will be it will be directly proportional to small r, right? Small r, it is directly proportional to small r, means small r and small r is r minus d. So it means as r minus d increases, G will increase. So it means when we go at the depth, G will decrease, and at the center G is taken as 0. Okay, so and here we can also find out the percentage change in gravity by using simple formula, change upon initial into 100. So it will be percentage change with depth, final which is G minus G d upon R. It is final term, and minus initial is at surface upon initial into 100. So here the remaining term will be minus d upon R into 100. So this negative sign shows that acceleration due to gravity decreases with depth also, right? So now when we plot the graph between graph of G with R, small r, net distance of the object from the center of the earth, then suppose on x-axis we are considering here small r, and at y-axis we are considering small g, and suppose it is the point where r equals to r, means at the surface, and as we know at the surface acceleration due to gravity G is maximum. Suppose it is 9.8 meter per second square. So it is the point where g is maximum. Now when we go at the distance, r is less than r, means with depth, and by this we can say as r decreases, r minus g decreases, then g will decrease, and it is the dependence on of gd on r as power 1. So the shape of graph will be simply a straight line, right? But now when we plot the graph of g for the distance greater than capital R, means with certain height h, then we have already calculated it that g at any height h is depend on the small r, means r by r plus h as the inversely and power 2. So shape of graph will be like this, means 1 by r square and r. So in next class we'll discuss the effect of the acceleration due to gravity with a certain latitude theta, and in the next topic will be orbital motion. Okay, thank you.